We'll start the today's lecture now. So far what we have discussed about the stability, some definitions of stability and some key theorem which gives us the necessary and sufficient conditions for the stability. We also see some couple of tools to analyze the stability, the root locus within the state space and also the Routh-Hurwitz criteria. So today we will be starting with the frequency domain techniques, that how you can determine the stability of your closed loop using the frequency domain techniques. So before starting this, let's discuss, or let's spend some time on discussing the concept of the frequency response, that what do we mean by the frequency response and how is it different from the other method we have taken, the root locus. Okay, so let's take this question, the interaction session first. Yes, RCPITMH.
Hello, sir.
Yes.
Sir, what is effect of gain on stability of control system?
What is what?
What is effect of gain on stability of control system?
What is the effect of gain?
On stability of control system.
Okay, I see. So when you say about uh, the effect of gain, you need first think, or I suppose that it is clear in your mind that we are talking about the gain of the control system of the controller itself. There could be a gain constant in the planned transfer function as well. So we have discussed about this Routh-Hurwitz criteria and also the root locus technique, where we saw that with respect to one variable or a number of variables, we can see that how the stability of the closed loop will going to affect. So if we have a constant gain in the controller, let's say we denote this by K, capital K, then using this gain we can plot our route, we can make our Routh-Hurwitz table or plot the root locus technique to see that how the stability will going to affect.
Thank you, sir.
Okay, so we'll start with our frequency response. So what do we mean by, first of all, the frequency, the response, and how is it different from the other method we have discussed so far? So since we are concerned about the steady state, about the equilibrium points, so what we say that when we apply a sinusoidal input to a linear system, it generates a sinusoidal responses of the same frequency. Okay, but what differs between the input and output is basically the magnitude and the phase angle, which are as a function of frequency. So if we see in this figure, we have this basic system, a mass damper system, where the spring is loaded in parallel with the damper and we have a mass associated to it, attached to it. So if we apply an input in this direction, a force and function, which is a function, which is a sinusoidal function with frequency omega and phase angle phi of I. So when I apply this input to the system, basically this system, if you start modeling the system, it appears to you as a second order system. Okay, so once you apply this input to the system, it will give you this kind of output, where you see we have a capital M naught, the magnitude, and a sinusoidal function which is having the same frequency as the input function, but it differs only in the phase angle, which is the phi of phi naught. So what do we mean? Let's see. So we apply an input which has a magnitude mi with the phase angle phi I. It gives me the output which is having the same frequency. It is of the same frequency, but it differs only in the phase angle. Okay, and note that why we are calling this the linear system, or why, or the property of the linear system where it is hidden in, that these constants, this m naught, or let's not call them the constants, this the amplitude, the mi and mo, are just the function of frequency, they are not the function of time. Similarly goes for the phi I and phi o. So these two things are also the function of omega, what you see here. So if they are varying with respect to time, then you cannot call them a linear system. So assume that the system is represented by this complex number. It is a generic representation where we have the amplitude, which is a function of omega, and the phi, which is also a function of omega. So the steady state output is basically given by this thing, where where this MO is being modified to the multiplication of MI and M, where M is basically your system, right? If you see in the last slide, basically this system can be represented is basically the same thing, M of omega and the phase of omega. Okay, so the output phase difference is basically the summation of these two things, the initial phase angle and the phi which is induced by the system itself, and the output the magnitude of the output signal is the multiplication of the magnitude of the input signal, this one, with the the magnitude of the system itself. So we can differentiate between these two things, where we call the phase frequency response and the magnitude frequency response. Okay, this M and phi, if you compute from this above equation, it will basically give you this thing. So what do you see here? The idea is to construct these two functions, the magnitude response and the phase response, which are basically the function of frequency. And then when you plot these two functions, then you try to make out some property out of it. And when we do this analysis, basically this gives us the stability analysis. Okay, so about this analytical expression for frequency response, you can see the lecture notes. We won't be deriving here, but it is not that difficult. The idea here that, or you can consider this example, where you are applying a sinusoidal input to the system, and once you start taking the Laplace transform of this one, the system itself, and whatever the output you will going to get is, you can have this separate the magnitude response and the phase response. Okay, so this is what I mean by the analytical expression for the frequency response. When we have this magnitude response, or the functions, the mathematical functions for the magnitude and the frequency response, there are two popular ways to plot them. One is a Bode plot, which are the function of frequency, where we separately draw the magnitude response and the phase, or the phase plots. What do you see here in this Bode plot? The frequency, which is on the x-axis, is plot on the logarithmic scale, while okay, these two plots are plot on the logarithmic scale. The phase is generally the degree one. Okay, so this plot is just an example for this GS is equal to 1 upon S plus 2. So if we see very quickly for this one, that how you can plot this two things, let's go here. We have this G of S is equal to 1 upon S plus 2. So what do we do here? We replace this S by J omega only. Why do we do this? Because here we are concerned only with the frequency response which have a purely oscillation behavior. So in the initial one, we are also calculating the frequency response. We simply replace the S is equal to J omega, and then we try to see that how the oscillations will going to behave. So this is what we compute. Okay, this you can differentiate out between the real part of G J omega plus the imaginary part of G J omega. Okay, then you can compute the magnitude response, okay, which will eventually come out okay, and simply you compute the phase difference of this J omega, which is nothing but the tan inverse of imaginary part of G J omega and the real part of G J omega. So these two things you plot, but not you plot the phase response in this way, in that Bode plot. But while plotting this magnitude response, what do? You compute the magnitude, the absolute value of G J omega, and then you plot the 20 log of this magnitude. Okay, this is on base 10. So this is what plotted here. So we're going to see much in detail with how you can plot this systematically. Another popular way is what we call the polar plot. Okay, in this plot we do not have two separate magnitude response and the phase response. Only in one plot we can plot both the responses. Okay, notice the x-axis and the y-axis here. So far we were discussing about the s-plane only, where the y-axis is simply the imaginary axis, and the s1 the x-axis is the real part of s. But here what we are plotting, the real part of g against the imaginary part of g. Okay, so let's say I have this kind of plot which start from omega is equal to 0 for this function. Okay, for omega is equal to 0 we plot until we get this omega is equal to infinity. So suppose if I'm at this position, okay, I draw a phasor. Okay, I draw a phasor. Then in this phasor, both the information about the magnitude response and the phase response is inherited. Okay, the magnitude of this phasor will give you the magnitude response, and the angle with which, and this angle will basically gives you the phase response. Okay, the phase angle of this point at omega, let's say omega is equal to 4 radian per second. So if we want to see that how do we draw this plot, we can see very quickly. If we have this gs, the same gs 1 upon s plus 2, we replace this s by j omega, which gives me j omega plus 2. Okay, in a similar way, how you can separate the real and imaginary part. Okay, this is your g of j omega basically, and then you can separate out the imaginary the real part, which is 2 4 plus omega square. Okay, minus of j omega. So I give this as the x-axis, and this one, including this negative sign inside, okay, give me the y-axis. So these two plots are being, this is how it is plotted, this real part of g and the imaginary part of g. Now if we have a more complex transfer function, then how we can draw the Bode plot in a very easier way. So there are a couple of points which say the log magnitude and the phase frequency response curves as functions of log of omega. The most important point is the third one, which says the straight line approximations simplify the evaluation of the magnitude and the phase frequency response. So what does it mean? So let's go to the, okay, now what do you see here, that the magnitude of this g of s is basically given by this relationship. Okay, and this is nothing but a function of omega, right? And these, since we are talking about the linear system, so when you start plotting this function or this mathematical function, okay, generally get the smooth curves. So and when we say that the straight line approximations, what we are doing, okay, so let's go back to this one. We'll see in this next slide what do we mean exactly by the straight line approximation. But the point to be noted here is whenever we have a function which is a function of frequency, as we have seen for the phase response and for the magnitude response, they are generally the smooth functions of omega. So you see here, so if we consider this g of j is simply which say that we have a 0 at the origin. Okay, if you start plotting this function, okay, you will be of course going to get a straight line, right? Because it would be what, right? If we have the g of s is equal to s, putting s equal to j omega, we'll get this j omega, right? If we compute the magnitude g of j omega, you will get what, omega only. Okay, so it would be a straight line, right? But if you have a more complicated function, let's say instead of this one we have this omega square or some omega cube, okay, they would be generally smooth functions. So those function also we can approximate by the straight line while plotting the Bode plot. We'll see, this is what we're going to see in a couple of other slides. So what it says, so if I have this g of s is equal to s, okay, let's go back to here once again. So if I take put this m, I take the 20 log base 10 of m, it gave me what? 20 log base 10 of omega, okay, which says, and this is my x-axis, right, and this is my y-axis, which says y is equal to 20x, where 20 is nothing. If you see that the equation of your straight line, y is equal to mx plus c, okay, this m or 20 is basically the slope. What is mean here, that we have a slope of 20 dB starting from 0.01 frequency. So what it says, so whenever we have a function, or whenever we have a function which say that we have a 0 at the origin, it will going to contribute a 20 dB per decade of slope in the overall Bode plot. Now speaking about the angle, if I compute the angle phase of g of s, it would be what? Tan inverse omega over 0, because I don't have the real part. The real part is 0. So this will give me tan inverse infinity, which is equal to 90 degree. So this is what is drawn here, that the contribution of the phase is basically 90 degree. And if I have the inverse of this s, that is to say, if I have a pole in the transfer function at 0, it contributes to minus 20 dB per decade slope, and it will contribute minus 90 degree. So this is some couple of example for the first order polynomials. Now let's say if I have a g of s which has a root or a 0 other than 0, other than located at 0 position. So if here we have the s plus a. So if you write this s plus a in a similar fashion, we have this g of s plus a, okay, s is equal to j omega. This would be j omega plus a, or you can normalize it to, let's say, a j omega plus a plus 1, and this would be your, let's say, a new frequency called omega prime. So now you have this a j omega prime plus 1, right? So for this you can compute separately your magnitude and the phase, which is given over here, that it will start contributing. You see, we have the frequency by a, okay, it will start contributing the 20 dB slope at 1, because what it says, for omega, whenever we have the omega which is very less, okay, whenever we have the omega which is very less, right, if I have this omega is of very less value, then the contribution, right, meaning to say, for omega very less than equal to 1, this would become what? This function on the right hand side, the right hand side will become to 1. Then if you take the 20 like base 10 of 1, of course it will give you 0. So here we are concerned about at this position, okay, if we have the frequency which is very less than 1, then the contribution of the slope is nothing but 0. But after that, when the frequency will start dominating, okay, we would have the plus 20 degree dB per decade slope. Okay, similarly goes when we have a 0 pole at minus a, we will have a contribution of minus 20 dB starting at 1. Because if you notice the x-axis, my graph is already in the log scale, so it is sufficient to write the frequency as it is, right? Okay, so let's, yes, so okay, so if we have this one here, there cannot be that too much gap, okay, from 0.1 to 1, and the same gap between 1 to 10. No, frequency is 1, because the plot is already in the log scale. The plot is already in the log scale, so whatever the frequency is written over here, they are the absolute values without taking any logs. Okay, but on the y-axis we have the magnitude which is written in the log. Okay, we'll take these questions whatever are there in the chat or in the question window after we finish this basic concept of frequency response. Okay, So now for this, if I have a 0 at, let's say we have this function, okay, this makes a contribution of 45 degree per decade, and this makes a minus 45 degree per decade if I have a pole at minus a. We will see that how we can use this separate functions or separate analysis for our more complex transfer function. So let's say we have this example here where the g of s is given by this, where it has 3 poles located at 0, -1 and -2. Okay, I have a 0 which is located at -3. Okay. So we need to draw the Bode plot. So first what we are going to do, there are basically two ways to solve it. Either you make it as a function of frequency, you separate them out, the frequency response and the phase response, then you, as the frequency is varied, you plot those functions. Okay, otherwise there is a quick way to plot them as well, which we are going to see now. So for this we need to do some, to draw the basic table. So let's say, how do we do it? First we identify all the location of poles and zeros, because these poles, the poles and zeros are basically the breakaway points. So we make a table for drawing the magnitude response. We have a pole at 0, we have a pole at -1, we have a pole at -2, and we have a 0 at -3. So we put this on this for making the columns, and then we go, because the plot is starting from where, from 0.01. Okay, but we can have a, or basically what do we do? First we write this, the location of the poles, the values as well, the 1, 2 and 3. Then we go a decade behind this 1, which is basically 0.1. So we know that the pole at 0, this pole at 0 contribute a slope of -20 dB, and this -20 dB is for the rest of the breakaway points. So we start from here, -20 for this, for this, for this, for this as well. And the pole which is at -1, it will start contributing its slope of -20 degree from this point only, and it won't be having any effect on the previous breakaway points. Okay, similar, and then it proceeds further. For pole at -2, it will start contributing at this location. The 0 at -3, it will start contributing from this, but the positive of 20 dB. So when we sum them up, this is the total slope, and these are the breakaway points while drawing the magnitude response. And this is how our magnitude response looks like. We start at 0.1. Okay, from 0.1 up to 1, it has a slope of -20 dB. Okay, so from here to here, I have a slope of -20 dB. From 1 to 2, I have a slope of 40 dB. Okay, from 2 to 3, slope is -60 dB. These are the logarithmic plot. So whatever the vertical lines you are seeing here is basically the frequencies. And from starting from 3, I have a -40. So this is how you can draw your blip plot without writing them as a separate function of omega. Okay, and this is what do we mean by the straight line approximation, because once let's say if you want to plot this any mathematical function as a function of frequency in MATLAB, so if you plot this function, it will give you the smooth curves, okay, basically at these breakaway points, right? And this is basically a simple approximation using the straight lines, right? But the analysis what you are going to get using the straight line or the smooth line will going to remain the same almost. Okay, the procedure for now plotting the phase response is a bit different. So what do we do here? Again, we write the poles, and these are the breakaway points, like I said. But I know that if I have a pole at S, the contribution by this S is -90 degrees. So there is no point to write it here. We start with those locations which are other than zeros. So -1, -2, this is basically the 0. Okay, so we assign a start position, then we assign the end position a decade after. Okay, so if I have a, so we start at 0.1. Okay, it will start at this one, it will end at this location from 0.2 to 20.3 to 30. Okay, a decade before, a decade after, right? Okay, let's rub all this thing to make it more clear. So let's see once again, what do we do in this while plotting the frequency response? That first, because we know that these are the breakaway points, the location of the poles and zeros. So first we put them on the first row, right? While plotting the phase response, we also assign the start position and the end position or at the location, or let's say at the breakaway points, a decade before and a decade after. So we start at 0.1 up to 10, 0.2 up to 20, 0.3 up to 30, right? And I know that whatever be the location of the pole or zero, it will going to contribute minus 45 in case if it's a pole, plus 45 in case if it's a zero. Okay, so the pole at minus 1 start at 0.1. Okay, it will contribute minus 45 degree of slope, continuing until its end at 10. Okay, 10 frequency at 10 radian per second. Similarly, pole at minus 2 start at this point, and at this point 0 at minus 3 will have a contribution of positive 45 degree starting from this one and finishing at 30 radian per second. Then if I add them up, I will have a total contribution of the slopes while for plotting the. So this is how it looks. We start at minus 90 because I know I have a pole. So similarly 45 degree from 0.1 to 0.2, this is 0.2 scale. Okay, this is 0.3 up to 1. So 0.2 to 0.3, I have 90 degree. So similarly it goes on, right? So this is how you can quickly draw the Bode plot whenever you have a transfer function, right? You need to do a bit of bookkeeping, and then once you have a table associated with the transfer functions, you can have a Bode plot. Okay, for second order polynomials, there are other things which are associated to it other than the stability, though we haven't discussed the stability so far using the Bode plots. But once you start plotting this such kind of functions, you start seeing these peaks, and these peaks have some significance when you will going to study the transient response later on. Okay, for the stability, for analyzing the stability, these peaks generally do not matter. So for second order response, we have such kind of peaks. When you have a second order system, basically poles without any zeros. Now comes the important concept about the stability using this Bode plot. So let's say I have a Bode plot which looks which has this magnitude response and the phase response. So first of all, what do? I compute the margins, and these margins are called the gain margins and the phase margin, or basically the two margins which plays an important role for computing the stability. So what it says, whenever this phase response crosses this minus 180 degree line, okay, I go above and see that what is the magnitude of this. Whatever the magnitude is, this one will give me the gain margin. Now, and this frequency is called the phase crossover frequency, where it crosses the minus 180 degree. Then in the phase plot, in the magnitude plot, I see that what is my gain crossover frequency, where it crosses the 0 dB line. Then the 0 dB line, since it is drawn on the same frequency scale, I can go downwards and see that what is the phase margin of this transfer function. So now this region, the region above you see at 0 dB line, if you have a gain margin, this gain margin falling in this region, then your system is unstable. Then your system is said to be unstable system. Okay, similarly, if your phase margin is in this region, then it is called an unstable system. Okay, so we can see if our gain margin is this one opposite to the unstability, we have the stable region. Similarly for this one. So for this transfer function, you could easily see by computing the gain margin and the phase margin that my system is stable. And what flexibility it also gives you, okay, we will see in the next couple of slides possibly. So when you first, the idea is you plot the Bode plot using the transfer function given to you, and then you compute the phase margin, gain margin, and these two crossover frequency. For this also you do not need to first plot the response. You can also do this mathematical calculations that at what value your frequency function, which is a function of frequency, crosses this minus 180 degree line. Similarly, for your magnitude response, at what frequency it crosses the 0 degree line. And at those frequency, you can compute your margin. It's not really necessary to draw the Bode plot. Once you have a plot, okay, it gives you more visualization. So let's see, I have this one example where the GFS is given by this and my K is unknown to me. What I know here, the location of the poles only. So let's say I fixed, generally you fixed the all the parameters in this transfer function are generally known to you. Otherwise, if they are known, you cannot plot the Bode. Either you assume it K is equal to 1. You can use other values, like here I have chosen this 40. So if when I choose this value 40 for this G of S, this is the Bode plot I get for this transfer function. Then I compute the phase crossover frequency and the grain crossover frequency. So for the phase at this 718 per second, I have the phase which crosses this minus 180 degree line. And then I see the gain margin. Since I'm in this region, and basically you won't be going into the positive region because your graph itself start from. So here you see that when you choose the value 40 for this gain K, your system is stable. Now you also need to know that what would be my range of K that I can say my system will be stable within this range of K. So once you compute this, the gain margin minus 20 dB, what says, okay, let's see what it says, that an increase in gain of 20 dB is possible before the system becomes unstable. So you can you have the flexibility of increasing the gain K or decreasing the gain K, so that you always stay within this region which is below this one 0 dB line. So how to compute the gain K? So so from the plot it says I can have a plus 20 dB the extension, okay, which allows me that my system is going to remain the stable, right? So the 20 gives, let's put this some gain G. From this it gives me G is equal to 10, and this is the factor by which I can increase my this constant K, the gain K, which gives, since I choose this 40, okay, and multiply by 10, okay, it gives me 400, right? So the range of K would be from 0 to 400. Why 0? Because like we have seen here that the graph itself start from 0. Okay, regarding this, before starting this Nyquist plot, let's take this some couple of queries or some. So it says DCEHY, what is the relationship between stability and coefficient of characteristic polynomial? Okay, we have seen this while this you can see by writing the Routh table, okay, because we have the conditions there which are basically the function of the parameters or the coefficients of the characteristic polynomial. So from there only you can have the conditions, right, to guarantee the stability for your system. What is the effect of feedback on the time constant of a control system? Okay, well, this is out of the scope first of all for this lectures, but okay, it's because for answering this question we need to define a couple of things: the time constant, the effect, and the feedback, right? The next question says, what do you mean by steady state error? Okay, by the steady state error, what do I mean? So let's say I'm here. So I'll try to explain it with the help of the with the plot. So let's say I apply an input to a system and apply an input to the system, okay, and I want, okay, so let's draw the system as well. Okay, this is my closed loop, C, E, this is my reference input, and this is my output response for this reference signal. And what I want, that the r of t is basically this function of time. What I want, that I want to design a controller such that yt tracks rt. Okay, so let's say if I'm having such kind of line, this one, okay, I don't know where to change the colors, but let's say I have this one graph, okay, for the response, and another one I have this one, okay. This is for one controller setting, and this is for another controller. So here what do you see, that my y of t, okay, approaches to r of t as the time t tends to infinity, okay, or let's say your y of t is equal to r of t basically at times t tends to infinity. But here if I see very closely, there is a gap. There is a gap which says your y of t is not equal to r of t whenever your time t tends to infinity. And this gap, let's say I call the error, and let's call the steady state error, because now I'm talking about the time when t tends to infinity, okay, which is a constant difference between the r of t and the y of t as t tends to infinity. Okay, this is what I mean by the steady state error. The error between the output and the input at the steady state. And the steady state what we are considering here, or when your system, we are considering at time t is equal to infinity. So it says can explain stability of system in terms of gain crossover and the phase crossover. Okay, so this is what do you mean, I guess, by the plot or by the margins we have seen. So at the gain crossover frequency and the phase crossover frequency, you computed the margins, and depending on that in which region your margins are falling, you determine whether the system is stable or unstable. Next question is why logarithmic scale is used while plotting the Bode plots. Okay, well, this is a sensible question, I would say. Why it's a logarithmic scale? Because you see here, uh, first of all, so let's say, in fact, the question is, whatever the question you have asked, the answer is within this question only. So let's say if I have a frequency, I have y, I have some another variable other than t, x, okay. So when I take this x, in the logarithmic scale, let's say log of x, okay, I can have the plot even when my x is very large, right? Even when my x is very large, and we are generally concerned about the frequency starting from 0 up to infinity. So we also need to see at very high frequency, at very low frequency. So if I use the normal standard scale, okay, I would need a bigger plot, okay, when we have the log plot, okay. You see, so if you say, if you have a frequency, let's say x, the frequency is 10 to the power 4, okay, you could imagine that how much x scale I would need. So when I use this log of x, it would give me the 10, sorry, 4, right? So imagine if you want to go from 10 to the power 4 to 10 to the power 5, okay, how much scale you would going to need. Similarly, this log of x would give you 5, and this is monotonic also from 4 to 5. So this is the basic reason behind using the log scale. While we do not use the log scale or any kind of logarithmic thing in the Nyquist plot, what we have seen in the initial slide, because there is no need of it. Okay, we'll take a couple of interaction sessions before we go to the break. Okay, please explain once again how to plot Bode plot for the function s over s plus 2. Okay, so this question is from BMSCE. Okay, so if you notice this, there are one pole which is located at -2, and there's 1 0 located at 0. So you can use the basically the same functions, okay, what it says. So you need to use these two things to incorporate in your final transfer functions, and similarly uh, for 1 upon s plus a, these two things, okay. So using these two characteristics, you can have your the Bode plot for this desired transfer functions, right? Similarly, by taking the by having this table first, or what do we say, by keeping a bit of bookkeeping for the magnitude response or for the phase response, right? But if we take this example very quickly, so what it says, this would help you also make the Bode plot for a given transfer function. So what do we do? First, we identify the location of the poles and the zeros, and these locations are basically the breakaway points in the Bode plot. Okay. So first we write all the poles and location here, and we start at 0.1. Let's say the start pole at 0, the start pole at 0. We have a pole at -1, -2, and -3, and all the frequency is associated to it. Okay, because these are nothing but the frequencies, right? If you write the s is equal to j omega, okay, these are the frequency which are associated by this function only. Okay, so we were here with how we can recalling that how we can draw a Bode plot for this given transfer function, and the same principle you can use to draw the Bode plot of other transfer functions as well. First, we identify all the poles and zeros, and these are the breakaway points. So identifying these breakaway points, we make this kind of table, and these breakaway points are nothing but the frequencies. Okay, so we start at 0.1, pole at 0, 1, pole at -1, 2, pole at -2, and 3, pole at -3. And then we start identifying the contribution of the slope with respect to each breakaway point. Okay, so if I have a pole at 0, I know that okay, for the magnitude it doesn't matter, but pole at 0 will have a contribution of -20 degree for the rest of the frequencies. Pole at -1 will start at -1, it will also have a contribution of -20 degree for the rest of the breakaway points. The similar analysis for -2 and 0 at -3, the difference is the contribution is now the positive of 20 dB. So once I add them up, it gives me the total slope with respect to each breakaway points. Okay, so first I then identify that where are these points located. So let's see, the poles start at 0.1 up to 1. I have a slope of -20. Starting from 1 to 2, I have this 40 dB, this one. From 2 to 3, I have 60, -60, and from 3 until when omega is a greater value, okay, I have a contribution of -40 slope. Okay, so this is for the magnitude, and for the phase, okay, it's a bit different. So again, we identify the breakaway points, then we go a decade behind and a decade after to identify the start position and the end position. For the phase plot, we have these two positions, while for the magnitude response, we were not having this ending position. Okay, so a pole other than 0 contributes -45 degree. A 0 other than located at 0 has a contribution of +45 degree. So in the similar way, we again build a table, right? And then we see a total slope, and finally we have a plot. Okay, and these two plots, the magnitude response plot and the phase plots, are drawn on the same frequency scale. Okay, the magnitude response comes at the top, and the phase plot comes at the bottom. So it is easier for us to identify the crossover frequencies and the margins. And depending on the margins, we analyze that whether the system is stable or not. Okay, so yeah, we haven't discussed about the Nyquist plot. Well, Nyquist plot and polar plot are basically the same thing. The significant of breakaway point in the root locus. Mm, well, it doesn't have any significance on the stability or instability, so difficult to comment on this. What type of system it will be if gain margin, phase margin, both are zero at the same time? Okay, so it is quite straightforward that if we have the gain margin zero, meaning to say that we no longer have any flexibility to change the gain constant, right? So it would be a marginal stable system in that case. Okay, so we'll take the interactions later on because we need to finish this Nyquist plot as well, right? Okay, so now next comes the polar plots. Well, this is the conceptually it is much more difficult than the Bode plot, though here we draw the plot as well, but the idea from where it appears from, the Nyquist criteria, is a bit complex. Basically, it comes from the complex variable analysis. So we're going to see now. Okay, so what it does, it relates the stability of the closed system to the open loop frequency response and the open loop pole location. We'll see this point in detail how. The knowledge of the open loop system frequency response, the knowledge of open loop system frequency response yields information about the stability of the closed loop system. So what do you need to, so what you will see here, that if I know, or if I know the location of the poles or zeros of the open loop system, then I can say, though I do not know the controller, I could have the information about the stability of the closed loop system, right? So try to think on this statement a bit more time. So let's say if I have a controller, okay, once I attach a controller to the within the closed loop system, okay, and now I just compute the open loop system response, meaning to say that if I have this closed loop, the feedback one, okay, I just need to see the forward path, that's it. I do not need to write the transfer function as a whole and see the location of the poles. Basically, you are not computing the location of the poles of the closed loop. Just by looking at the location of the poles and zeros of this open loop system, you could directly say that if this controller is in the closed loop, your system would going to be stable or unstable. Because in the root locus technique, we identify the location of the roots. Okay, we identify the location of the roots as well. But here we can directly speak about the stability. Okay, so using this criteria, you can extend the concept to the transient response and the steady state errors, though we won't be discussing about these two things because like I said, the very first performance criteria is the stability issue. Okay, so we'll give attention to the basic concepts. We're going to build a relationship between the poles of this, between the poles of 1 plus GSHs, okay, and the GSHs, the relationship between the zeros of this and the closed loop, the two main concepts, the mapping points and the mapping contours, okay, which comes from the complex variable analysis. So once we have all this the knowledge of these four concepts, we would be in a better state to give the stability conditions using the Nyquist criteria. Okay, so let's say I have this feedback loop where the G of S is my plant, the H of S is my controller. It is, you can rearrange it in a unity feedback closed loop as well. So if I have a transfer function of GS HS written in this way, the numerator and the denominator of G, numerator and denominator of H, this is how I can, of course, I can write my this forward path. Okay, the multiplication of GS and HS, and also 1 plus GS of HS. So you know from the earlier lectures that the closed loop is basically given by this one. Okay, G over 1 plus GS of HS. So now see here, that if you pay an attention to the poles of this one, that is to say the poles of 1 plus gs of hs, which is nothing but the roots of dg and dh, are similar to the poles of gs and hs, which is the dg and dh. Okay, and the zeros of this one 1 plus g and hs is basically the roots, the poles of this ts, which is our closed loop system. Okay, so we are going to see the relationship, that how we can plot the Nyquist criteria using this GSHS and 1 plus GSHS, and on the basis of this, what type of stability condition we can enforce, or we can derive from out of it. Okay, the poles of GH one, the same thing. Okay, now comes the concept of mapping. So what do we do here? So far we have seen the S plane. So the S plane itself is a complex variable plane, where S is nothing but the sigma plus g of omega, j omega, which has the real part and the imaginary part. So when we take a complex number on the S plane and substitute it into a function f of s, and this f of s could either be we will see, could be any function of s. Basically this could be this one or this could be this one, right? Because both these two functions are the function of s. So if we substitute it into a function fs, another complex number results, and these collection of points what we call the contour. So the idea is, if we have in the S plane, generally we have the location of poles and zeros of any function, right? Once I have the poles and zeros location, I make a contour A, which I specify by myself. Okay, then if I put this into a function f of s, I mapped this from contour A to contour B. Basically these are these contours. Okay, so this contour A is plotted in this way here in the F plane, and this F plane could either be your 1 plus GH plane or your GH plane itself, right? In the very first couple of slides, we saw that in the x-axis, we put the real part of the G of S, and the imaginary part was the imaginary part of G of S, right? Here G of S could either be 1 plus G of GH or GH, because basically it's a function of F, right? So that's why we call in general the F plane, and this F could be any function plane which you are specifying here. Okay, so this is how you map from S plane to another plane, F plane. We'll see while taking some couple of example. So this is the engine behind the Nyquist stability criteria. What do we say? If a contour big tau in the S plane encircle Z zeros and P poles of f of s in clockwise direction, basically the clockwise direction is associated to it also. Okay, in which direction it is circling. In the clockwise direction, the contour tau prime, which is the image of big tau as mapped by fs, basically this one, encircles the origin in the w plane, in the new plane, z minus p times in the clockwise direction. So this is the Cauchy's argument principle. So using that principle, we derive the Nyquist stability criteria, and this principle says this thing. So the only thing we are looking at is the number of encirclements of the origin. Okay, we know the location of the poles and zeros of, let's say, the G and H, G into H. Okay, and thus, and just by computing the number of encirclements of the origin of this counter in the new plane, we could say directly, we can speak about the stability. All right. Okay, so let's see what it says. If let's take a complex function f of s, which is given by this one. This could be 1 plus gh, right? Or this could be gh, your f. Okay, okay. So if we would apply this function to a complex number c, I take a complex number c, and this number could be any number in this count in this. Okay, this comes down to multiplying factor this one c minus zi, all these values. Here s I replaced by c, so I would have c minus z1, c minus z2, c minus z3, right? Let's say if I have the c1 and I have the c2, which I another or the same, of course the same complex number c minus p1, c minus p2, c minus p3. This yields this kind of the magnitude and the phase angle, and this is nothing but the modulus of this will result the modulus this one and the argument of this one. Okay, all the zeros, the magnitude of the zeros will come in the numerator, and the modulus of these poles will come at the denominator, and the ratio of this one will give the phasor length from the origin in the f plane. Similarly, this angle gives the phase angle or the phasor angle starting from origin, where all the angles of the zeros are being added in a positive way, and the poles are added in the with a negative sign. Okay, so let's see this on the mapping itself. Let's say these are the location of my poles and zeros, okay, in the S plane, right? Two poles are located here, sorry, two zeros are located here, and three poles are located here. Okay, so this is my, I choose this contour A. Okay, I choose this f of s by this 1 plus g into h. Then if I take a point here on this contour, I compute the magnitude from all the poles and from all the zeros. Then once I take the put it in the ratio, that the magnitude from the zeros is v1 v2 divided by the multiplication of the magnitude of the from the poles. So this gives me the phasor length, and the angle contributed by this one, okay, by this one will give me the phase angle. So finally this give me this angle. In similar way, I can take any point on this contour and plot this into the function plane, which is the 1 plus gh plane. Okay, and this is my, okay, we haven't come on to the Nyquist plot so far. It just speaks about the mapping from one plane to another plane and what kind of function I use for the mapping. Okay, now these 3 points, what we have, or the summary of what we have seen so far. We saw the z equals the number of zeros of 1 plus gh inside contour A. Only in contour A, the location of the poles and zeros, the exact location of poles and zeros. P equals the number of poles 1 plus gh inside the counter, and then we compute capital N, the number of counterclockwise rotation, is equal to P minus Z. Okay, so let's see one example. This is in contour A, this is the contour B in the f function, another plane, W plane, which is the function plane. So if you see at this plane, what it says, I have 4 zeros and 2 poles. So z is equal to 4 and p is equal to 2, which says that n should be equal to 2 of the origin, and n is positive, right? So it should be clockwise rotation, because if you see z minus p is 2, and here p minus z will give you minus 2, okay, which would be clockwise encirclement of the 0. So finally, if you zoom it, the one encirclement I have from this axis, from this curve, and one encirclement is this one. So basically there are 2 encirclement of zeros in the complex function plane. Another example, if I have 2 poles and 1 0 inside this contour, p is equal to 2, z is equal to 1, n is equal to z minus p, which gives me minus 1, which says one counterclockwise rotation of the origin, which is given by this one. So this is how you map from one plane to another plane, another complex plane. Nyquist plot. Now we define a contour A. So far, whatever we have seen, the contour A was in very general. Okay, it works on the principle of Cauchy's argument. Now we converge it to the Nyquist plot, which says if I consider this contour A, this plot contour A in the S plane, and this is nothing but all the right half plane in the S plane. Okay, if a contour A that encircles the entire right half plane is mapped through GSHS, then the number through the information of the open loop poles in the right half plane equals the number of open loop poles P that are in the right half plane minus the number of counterclockwise revolutions A, which is given by this formula, and the mapping is called the Nyquist diagram or the Nyquist plot of. Okay, the Nyquist plot says now I dedicated a contour A which consider the right half plane. Now on the basis of this contour A, how can I can define the stability criteria? Now this is the main theorem which says if the open loop system, the multiplication of the plant and the controller, has L number of poles in the right half plane of the S plane, okay, then the system with unity feedback is stable if and only if the Nyquist plot encircles the point -1, 0 L times in the counterclockwise direction. So what it says, the first statement, if the open loop system has L poles in the right half plane, meaning to say that my forward path or the open loop system is already unstable, because I have some couple of poles which are in the right half plane. So when I close the loop, and see the Nyquist plot, if it should encircle, okay, it should encircle this -1, 0 L times in the counterclockwise direction for the closed loop system to be stable. So far we are discussing about the origin only, but from where it comes this -1, 0 point? Why all of a sudden? Because it is nothing but just a shift, because there we were considering about 1 plus gh, the function f. That's why we are considering about the origin. Now we are considering the open loop system as a multiplication of the plant and the controller. So that's why this point has been shifted to -1 instead of 0. Okay. So some couple of remarks that if the system is open loop stable, now if the system is open loop stable, if we pay attention to this theorem, then there should not be any encirclement for the system to be stable, right? If the open loop is stable, then for the closed loop to be internally stable, it is necessary and sufficient that under no unstable cancellation, the Nyquist plot of G naught C does not encircle the point -1, 0. Okay, pay attention to this some couple of words what occurs here, that first of all there should not be any unstable pole zero cancellation within this G naught CS. What does it mean? It almost mean the same thing what we were discussing the last time possibly. Let's see very quickly, that if I have a G naught, okay, which has 1 upon S minus 1, and if I choose the controller this S minus 1 upon S plus 1, then what it says, if I'm going to plot the Nyquist plot of this G naught C, right, it will give me what? This will cancel out and it would be S plus 1. And if I use this condition under the Nyquist stability theorem, that now there is no poles on the right of plane, the result would be wrong. So I need to consider these pole and zeros as it is while plotting the Nyquist plot and analyzing the stability under that theorem. Okay, so if the system is open loop stable, then the Nyquist plot of G naught C should not encircle the point -1, 0 at all. If the system is open loop unstable, it is the similar condition that it should encircle the -1, 0 P times counterclockwise. Now, if the Nyquist plot of G naught C passes exactly through the point -1, 0, right? If it passes exactly through -1, 0, then the closed loop has poles located exactly on the imaginary axis. In that situation, we say of the critical stable system. Okay, and the critical stability condition, we can generally consider the integrators. So we can see some couple of example for determining the stability using this criteria. Here we use this contour A, which has the consider the right half plane. So here in this first example, you see the P is 0. Okay, we draw the plot. Okay, in the GH plane. Okay, we see that the -1 has not been encircled. My open loop is stable. There are no encirclement. So when I compute the Z is equal to P minus N, it gives me 0, meaning to say that my system is stable. Now there are two open loop what it says, the poles of closed loop system. So there are P is what, the poles on the right hand side of the open loop. So my P is 0. If I see the number of encirclement in the GH plane, it says 2 clockwise encirclement. One is this one, another is this one. Okay, which is n is equal to -2. So when I compute the Z is equal to P minus N, which gives me 2, meaning to say I would going to have 2 closed loop poles on the right hand side of the of course of the closed loop system. Okay, so this is my unstable system and it is your stable system. So there are some slight modifications also when there are open loop poles on the imaginary axis, like this one. How would you going to encounter them? Either you detour to the right, because you need to see the behavior of these poles either within the contour or outside the contour, right? So generally we consider this one because the idea is we consider only the right half plane. So if I consider uh, this contour, it consider these on some portion of the left hand side. Okay, so generally we consider this region which messes out the poles which are located purely on the imaginary axis, right? And then we analyzes the stability in the similar fashion using the same theorem. Okay. So now if the closed loop system has a variable gain in the loop, then for what range of gain is the system stable? Since our main interest from the beginning, we want to see the range of some unknown parameters within the either in the controller or in the grain in the plant, that for which value or for what range my system is going to be stable. Now how the question arises, now using this Nyquist criteria, how can I compute basically the range? Okay, so let's see this example. So what it says, we have the one closed loop where it says two zeros which are on the left hand side. There are two poles on the right hand side of the open loop system. So if the open loop system contains a variable gain k, this gain k will follow this in a similar way what we have followed for the Bode plot. We consider either k is equal to 1 or some value to sketch the Nyquist diagram, and then we adjust the value of k to yield stability based on the Nyquist criteria. Because we have seen the criteria, so either we increase or decrease the value of k to see that how our number of encirclements are going on. So what it says in the S plane, I have this 2 and 4 poles in the right half plane, 2 zeros, -5 and -3. Then I make the contour, or I map this thing into this GH plane. So what does Nyquist stability criteria says to me? Now there are two poles on the right hand side, unstable poles. So there should be how many times encirclement in the GH. Once you start increasing or decreasing the value of k, you would see that this point is either not being encircled at all or circled 2 times. If it is not encircled for some particular value of k, it means that your system is unstable, because for stability there definitely should be 2 encirclements in the counterclockwise direction. Okay. There are also the gain margins and the phase margin you can compute using the Nyquist plot, and this again gives you the flexibility or the range of the variable before you enters into the unstable region. Okay, so for example, you have the Nyquist diagram for some transfer function. What do? You make a unit circle. Okay, you make a unit circle and then see at what point on the unit circle this plot crosses. So at the point it crosses, you measure this angle. You measure this angle alpha, which you call the phase difference before instability. Now you see that this plot crosses on the real axis. The point at which it crosses the real axis, let's say this minus 1 upon a, okay, or let's say this minus a, okay. This is the gain difference before the instability. Okay, that you can increase the gain difference before the instability occurs, and the gain margin in that case is given by these two formulas. Basically, these gain margins, or the what we call them the stability margins, are helped to in analyzing the robust stability of the system. And when I say the robustness, we'll see this robustness in possibly in the next couple of slides. Okay, so this is how we compute basically the gain margin, the phase margin, using the Nyquist criteria. Okay, we'll skip this one. Now talking about the robustness, this is a very brief description about the robustness. So what we have covered so far, that the transfer function of the plant and the controller is given to us, and when there are some uncertainties, because so far what we have seen that generally the exact model of the system is not known to us. We do the first principle modeling, we have the nonlinear equation, then we linearize them, and after linearization we get some transfer functions. Okay, so if there are some uncertainty in the parameters of the nonlinear system, it will going to reflect in the transfer function also. Okay, so there we say that it is an uncertain plant transfer function, not a nominal one. Okay, so however in practice we are usually interested not in only in the nominal performance, but also the true performance achieved when the controller is applied to the true plant. The transfer function of the controller is known to you because you are the control engineer and you have designed that controller which gives you this particular transfer function, okay, to be applied onto a physical plant, for which you have a model in terms of a transfer function, and which might be uncertain. Okay, which might be uncertain. So there you see the robustness of the closed loop with respect to that controller. Okay, this is what you all call about the robustness issue. Okay, that if you apply this controller, that how robust this controller is, there then you define the uncertainties within the plant. Then what type of uncertainties are? Okay, we will see that first of all we have seen these sensitivities, the gang of 4, that if I have a we have derived the very first stability condition based on these sensitivities, which consider the nominal model, right? So if we have a if we have a plant or the G which is different from this G, if it is different from this G, then all the sensitivities will going to change, and there your stability will going to affect as well, though you have derived the stability condition for a nominal system. Okay, so in general this G of S is not equal to the G naught, then in that case all these nominal sensitivities won't be equal to the, or these sensitivities will not be equal to the nominal sensitivity functions. So now the uncertainties what I was speaking about, these uncertainties are generally added in the plant. Okay, and either they add as an additive one, and these three are basically the same thing. Okay, if you have model, this is how you model generally the uncertainties, in an additive way, in a feedback way, or in a multiplicative way. Okay, so let's say this very first quickly, that what I mean. So if I have a plant, okay, let's say I have a plant P, a nominal plant. Okay, I derived all the all the sensitivities, I put forward my all the stability conditions. Okay, now my plant P is not P naught, but my plant P is some P naught plus some delta, some delta. Okay, now if you have this P, your all stability condition will going to be changed, and you don't know whether your system will become unstable possibly. Okay, and this is going to say that if you have this P, this is how you can model them, delta. Okay, so this is nothing but P plus delta, right? The uncertainties in the system could also occur in this way, where you have this P, this one, and in that case it is generally called the multiplicative one, where let's say this is your P naught, right? In that case your P would be what? P naught uh, 1 plus delta, which is P naught plus P naught delta. Okay, delta is a multiplicative modeling error. Okay, if this delta is equal to this big D delta, then you can have a direct relationship among them. Okay, so you can equalize them once you have some relationship between the small delta, big D delta FB, and this big D delta as well. Okay, so you need to once you model the uncertainties as an additive uncertainties, then you can generalize them as either feedback uncertainty or multiplicative uncertainty, right? So now the main theorem comes, which says consider a plant with nominal transfer function g naught of s and true transfer function given by g of s. Okay, assume that cs is the transfer function of a controller which achieves nominal internal stability. We have seen the stability conditions for the nominal internal stability. Also assume that g of s into c of s and g naught of s, c of s have the same number of unstable poles. Okay, what it means, that though there is some uncertainty in the plant, okay, my assumption says that this uncertainty retains the unstable poles within the true transfer function of the plant. Okay, then a sufficient condition for stability of the true feedback loop obtained by applying the controller to the true plant is that this one, where G delta is the frequency response of the multiplicative modeling error. Okay, first understand what this theorem says or what all assumption it makes, and then based on what it gives the stability conditions for the robustness. So you can directly prove this result by using the Nyquist stability criteria what we have discussed. So let's go very quickly. So first of all, what I have assumed, write them here, that the G into C and G naught into C, the nominal loop is stable, okay, and the same number of unstable poles. Okay, this are the two assumptions which I make. Okay, also this is my point 1, this is my point 2. See that the real loop, if we go to the stability theorem for the Nyquist stability theorem, it says the real loop is stable if and only if the Nyquist plot of GC encircles the point -1, 0 the same number of times and of course in the same direction as G naught C does. Okay, this is what my Nyquist table based on the Nyquist stability condition it says. So let's look at the Nyquist stability, for example the Nyquist stability curve. This is my G naught, the G naught into C, the Nyquist plot of this one, and this one is for the GC. You see that how the Nyquist stability curve changes, and now once you see this, if you go back to the previous one where it says the G delta is the frequency response of the multiplicative modeling error. Now what I assume that the G into C is your G naught C plus G epsilon into C, where G epsilon is your additive modeling error. And from the previous modeling principle, I know that my G epsilon is nothing but G naught G delta, where G delta is my MME. Now we go once again to the figure and uses the Nyquist stability condition. So see, this phasor is what, G naught C, okay, and this phasor is -1, right? So this phasor would become what? 1 plus G naught C, or what? Let's see once again. Okay, so this is my one phasor, right, which I know. Okay, from here I know that the uncertainty is this one, which is given by this additive through additive modeling error, where the multiplicative modeling errors is inbuilt. Okay, so my this phasor this phasor should be less than this phasor, of course, otherwise it will going to cross the -1 comma 0 axis. So this is my next equation from the plot, that your G epsilon of C, the magnitude of this one should be less than the magnitude of 1 plus G naught C, otherwise it fails the Nyquist stability condition what I have in the above steps. So my G epsilon, if I put this G epsilon by this one, I will have, go to the next page, I put this G epsilon is equal to G naught G delta in this equation, G naught G delta C of mod less than 1 plus G naught C for all values of omega plus. Okay, this gives me the condition G naught G delta C 1 plus G naught C should be less than 1 for all omega, and this is nothing but the same stability condition what I have in the theorem. Okay, so from the Nyquist plot you can also analyze the robustness of your controller. If there are some uncertainties in the plant, your plant is not a true plant what you have identified. Okay, now the following lemma from this theorem, that consider the nominal sensitivities and a plant with multiplicative modeling error with this G capital D delta, then the achieved sensitivity function are this one, and these are straight, the proof of this is pretty much straightforward. Once you substitute the G with the G delta, right, we have this sensitivities, right? If you substitute this G of S by the G of S what we have assumed in the theorem, you will going to get these results straight away. So these would be the achieved sensitivity function. Okay, so this is what all we have for the stability analysis. We are already extended from our usual time, but we can take some couple of questions and some interactive sessions also. Okay, there's a question from IJC What are the frequency domain specifications? Well, this is a very interesting question because we haven't considered this kind of frequency domain specification explicitly. So these kind of specifications generally come when you design a controller. Here what we are considering the sole specification as the stability. Okay, so just to give you a hint on this frequency domain specification, we generally give the specification in terms of the frequency. If we want, because if there's some noise of high frequency noise are being added into the system through the within the closed loop, then you give the specification generally depending on that within that frequency band your noise should not have any effect on the closed loop other closed loop specifications. Okay, and generally you give this such kind of specifications using your sensitivity functions, using all four sensitivity functions.
Good afternoon, sir.
Mhm.
My question is, what is the correlation between time domain and frequency domain specification?
Uh, Say it again.
What is the correlation between time domain and frequency domain specification?
Okay. I see. Generally, whenever you give your specification in the time domain, then like I was saying from the very beginning, here we are considering about the stability performance criteria only. So if you have any transient specifications which you generally give in time domain, okay, then you translate those specification in terms of in the frequency domain using the bandwidth of the closed loop system. So when you compute bandwidth of your closed loop system, there comes a relationship between using the settling time and the rise time. Okay, but those specification we take as a second step for designing the controller, and the very first one remains the stability, of course. Okay.
Question is, explain phase margin and gain margin.
In what, in the under the Nyquist plot or the Bode plot?
Both plots, sir.
Okay, so if I go back to the slides very quickly. Okay, so once I hope you can see the slides. So in the slides we have seen the rules for constructing the Bode plot. So once we construct the Bode plot, and for computing the margins, the stability margins using the Bode plot, we generally pay attention to the phase crossover frequency and the gain crossover frequency. And these crossover frequency are nothing but the phase crossover frequency. What do we say? At which it crosses this minus 180-degree line, and the gain crossover where it crosses the 0 dB line. So when we have the knowledge of these crossover frequency, we see from the plot both the phase margin and the gain margins, right? Like I said previously, you can also compute it mathematically without the help of this plot, okay, using this crossover frequencies. Okay.
Okay. Yes, sir.
Okay, so I guess almost all the relevant questions have been answered, and we are finished with this topic about the stability analysis for within the control system. I hope you have learned a lot. Okay, so we'll stop the session now. Thank you.